you slowly take a seat, we will start this edition of the Software Developer Thursday. So, welcome everyone to today's edition of the Software Developer Thursday. Today the topic of our smart specialization strategy will be our main pillar, the Open Data Hub, since today is here with us Matteo Roggia of the startup Animeshon, which helps us in the development of new architecture for the entire Open Data Hub, and so we will present, or he will present what we did in this first half part of the year. And we will be glad to discuss it with you and see if you have any question or suggestion for us to improve our architecture or what we thought. So I won't steal to Matteo much more time. Thank you, Matteo, for being here, and the floor is yours.
Thank you. Okay, so today I will show you the result of Animeshon's collaboration with Open Data Hub's team to design the new architecture of Open Data Hub. The content are many, the technology are even more. Therefore, I wanted to try a more like journey approach to show not only the result, but why we got to that result, what technology we analyzed, and why we choose the one will be the new Open Data Hub. So first thing first, who am I? I'm Matteo Roggia. I'm founder and CTO of Animeshon, a startup at the end of the incubation program here at Noi Tech Park, and I'm also working with Technity, another startup just incubated here in the Noi Tech Park. What is Open Data Hub? Anyone knows what Open Data Hub is? So, very long story, very short. Open Data Hub is a system which takes data from a lot of providers like Turismo, Autostrada A22, and many others, perform some transformation and data validation and manipulation, stores the data, and then serve the data outside. So as the name says, it's a hub for data. Those systems are particularly difficult to build because they inherit the problem of a consumer because they consume data from providers, and they also have to face the challenge of a data producer, since they have them to serve the data outside. Some of those challenges are they need to speak many languages in English because they need to aggregate data from different providers. Some speaks with JSON documents, others speaks with XML documents, some wants to push data, some wants to pull data, and blah blah blah. They also need, Open Data Hub needs also to ensure that data isn't lost once it gets into the system, because if Open Data Hub for any reason loses data, means that an end client which uses Open Data Hub will lose the information as well. Of course, complicated systems such as Open Data Hub have to handle errors at many levels. So when the data comes in, when the data is processed, when the data is stored, when it's retrieved, when it's served, and this is quite difficult to handle in a proper way. Also, we need to upgrade our system, because of course systems are continuously being developed, and we need to find a strategy to roll out updates without having downtime. Systems like Open Data Hub need to scale, because the more provider we have, the more consumer we have, the more traffic we have to handle. A system like Open Data Hub needs to be operable. What does it mean? It means that we don't have just to put it online. We also need to give the people, the developers, the engineers, the tools to make it run forever, ideally. It also has to be maintainable, because we need to fix things, we need to track down problems, we need to do whatever operation to make the system more stable, and it needs to evolve, because as we saw in the last 6 months, IT technology are running at a very fast pace. Like artificial intelligence is the proof that what we do today, tomorrow is already old. So we need to create a system which is able to accommodate the future challenge and the future technology. And also because we are Open Data Hub and we like to do things even difficult, we need to have, Open Data Hub wants to have all open source technologies with no vendor lock-in, so we can't have like a technology which is only provided by AWS or Google. We need to be cloud agnostic, because public administration has to be cloud agnostic, and we also decide, because why not, to store the data in the raw form, which means not only the transformed data, but also the data as it arrives from the provider, so that we can, for example, double check the transformation or repeat the transformation if something goes wrong. So yeah, let's start with the once we set our goal, let's start with the journey, and to make easier to understand how the system are built. Let's stop talking about data for a second, and imagine that Open Data Hub is a system which has the task to upload an image, to do some image transformation, store the image metadata, and allow users for image search, which is exactly what Open Data Hub does with thousands of different data. So, of course, someone could say, just fetch the image from Pinterest, for example, store it, and serve. But actually, it's not that easy. The real world is not that easy, because we need to fetch the image, we need to get the image metadata, like how the size, the resolution, the meme type, and whatsoever. We need to extrapolate the palette, because we want to do color search. We need to generate thumbnails, because of course we can't serve, for example, in a search result image, like 10 megabytes image. And because we are in 2023, we also want to use an AI model to find similarity with image already processed. And then we have to store everything in our database and then show the image in the search. Of course, a monolithic approach like this doesn't quite work well, where a service does everything, then stores, and then another service serves the image. So here we go with the microservice architecture, which is, I think, like the basis for an enterprise system. And the microservice architecture tells us that each operation has to be done by a single service which has limited responsibilities, has only one task, and he has to be pretty good at it. So we chunk the whole, like the big circle here, in many smaller circle. We fetch the image, then we pass the control to a service which gets the image metadata. Then we pass the control to a service which gets the palette. Then to one which generates the thumbnails, one which search for similarities. We store everything inside our database, and then we serve the image. But what if, like, the service which generates thumbnails goes offline for 10 minutes? So we have the image that goes for the first three circle and then stops because we have an error. So how do we address this problem? Because it's quite a big problem, because if in our pipeline there is, for example, the last step which fails always fails, we do have thousands of requests which completely fails just because of one single bug, and it's not good for a service like OpenData, which has to serve data or image in this case to our client, because the client will pay for our image sometimes. So the second, like, once we figure out that OpenData needed a microservice architecture, we had to address the problem of the nature itself of a big and long pipeline of transformation and sub-process which take place in OpenData, in this case for serving our image and in a image search. So I think event-driven architecture are a specialization of the microservice architecture where services do not communicate with each other through like synchronous communication. So it's not like that the central circle tells to other service to do things. In the event-driven architecture, we as a service, as a microservice, we do our job, store our result somewhere, and then we throw a message in the system telling, hey, I'm done, this is my result, so that other service can catch the event and take control of the flow and do their own job. So, for example, in fetching the image, we have the perimeter service, which is the one grabbing the image from Pinterest, which grabs the image, saves the image, and then tells, hey, I downloaded a new image. This is the location in an S3 bucket or a database or whatever. Do whatever you want. He don't even know who is the next in the chain. So the service responsible for the color palette, and the one generating the thumbnails do not know each other, but both react to the message thrown in the system, and they start doing their job. So in this architecture, there is a cause effect like system where once one service performs its job, it just tells the system he's done, and then it closes. Like it doesn't communicate with any other. In this way, if, for example, generate thumbnails fails, we still have all the other service going and processing the image itself, and they are already storing the result, so that even though we don't have, like, for example, a color palette, we still can serve the image in the image search engine, for example. This, of course, makes the architecture more resilient to errors, because we can, for example, have a service failing because it doesn't impact the whole system as a whole, but just its own task. And also exploiting what's called message queue. I don't know if any one of you is familiar with Amazon SQS or Google PubSub, but using those kind of systems, which are basically buffers where you throw in a message and then there is a consumer processing message one by one, you can put a queue before all of those systems in such a way that even if generate thumbnails for the service responsible for the thumbnails fails, the information that the image has been fetched is still in the queue because it's not yet acknowledged or deleted, what you want to call it. And when it comes back online, he can retry to generate those thumbnails. So this way we go through with those architectural choice, we got to a system which is distributed, where microservices do not have to do a lot of stuff, but just one and good. We design a system where even though something fails, he still can retry the process, and therefore is quite more manageable and operable, because if generate thumbnail stops to function, we don't have to reprocess the whole image batch. We just have to fix it and start again processing the message. And of course, a system like this, as you can imagine, it's very easy to evolve, because if we have to add more steps, or we want to I don't know, put an user input which helps other service to improve, we just have to attach more queues and catch the event already emitted in the system. So, for example, if you want to add an EI to flag restricted image, we just have to catch the same message as the one catched by the one generating the similarity rate, and we are good to go without any effort, like without telling to the system that we have a new service, you have to pass control to the new service, and then I'll wait for the result. And also we can, of course, instead of just fetching image, we can start fetching videos, because why not? We could say that the AI also analyze frames of the videos, so we can throw another message telling, I downloaded this thing, but it's not an image and it's a video. Whoever is interested in the video, do its work. So we also, in this way, we can also address the problem of speaking many languages in Ingress, because we are already speaking image and video language. So back to the real Open Data Hub. This is what the new architecture looks like. So every rectangle here is a service, and all rectangles communicate with each other through message brokers, which is the router stack here in the middle. So there's a lot of small services interacting with each other, but not knowing each other actually, because it's very rare that services communicate with each other. They are just part of a giant mechanism where you publish message and you capture message, and that's it. So, speaking about technologies we decided to use here, first thing, microservice integration, because of course we need a way to link all those lines are of course integration between services. So we have to find a way to pull message from the router, from the message broker, and push message. For example, we have to listen to the outside world with HTTP endpoints, REST API, WebSockets, and we need a microservice integration framework. So we choose Apache Camel, which is of course open source because it's on the Apache license. But what does it actually mean, integration framework? Because it was quite confusion on what did the microservice integration framework actually means. So a microservice integration is something that moves data from A to B, and that's the whole word an integration framework does. A could be a file, could be a REST API, could be a queue, could be a Google Sheet document. It takes the data, it can do some transformation, and then puts the data to be MP, again, can be a database, an endpoint, a file, or whatever. You could think, well, if this Apache Camel can do transformation, why do we even need to create service which transform data? We take the data from the provider, we do all our transformation inside Camel, and then we put that into database. Well, the problem with that is that if we need, for example, to fetch data from our existing database, like in the AI model to get other image similarities. So if the data coming from A is not enough, and we need data from C, for example, our database, it starts to lose its utility because we lose the very specialization of Apache Camel to move data from A to B and becomes somehow a general framework, and we do not want to use a screwdriver to screw a nail, so we have to choose the right technology for the right purpose. Apache Camel is written in Java, and it has a lot of those components which are the A and the B, so it has hundreds, if not thousands of integrations. It's written, he supports both XML declaration style if you like Java Magic, and if you like Java Magic but still with an imperative look, there is also another way to define those pipelines. And here we have an example of a very good example of Apache Camel exploiting. So the Apache Camel writer is an Apache Camel which takes data from a queue and stores the data in the database, and that's it. It doesn't do anything else. It just takes data from a queue and put it into the database, and that's what an integration framework should do. So we already said that at the center of Open Data there is a message broker, which is the one delivering and routing all the messages happening inside the system, and we choose RabbitMQ. The title is wrong. So we choose RabbitMQ. RabbitMQ is another open source tool which has the only purpose of taking message, routing message, and deliver message as the couple SNS SQS does, as Google PubSub does. But it's open source, so we are happy because we want only things open source. So yeah, there is how it works. Message in ingress, some routing, and put the data in the queue so that a consumer can do things. It speaks with the MQP 091 protocol, which is, I don't know if anyone is familiar with MQTT, it's like the version of MQTT on steroids. As I already said, it's better than MQTT, but it's worse. RabbitMQ is worse than Kafka. If anyone has had to deal with real-time data processing or big data, he for sure knows Kafka, which is de facto the state of the art of real-time data processing and big data. And if we had to use Kafka, we could replace almost everything in the architecture with just one tool, because it's capable of message broker, message routing, and whatsoever. It also has a lot of integration, so it could replace RabbitMQ, and allows for message aggregation. But there are two problems. So it's very hard to deploy, configure, and maintain, which, by the way, are already three problems. And it's even harder to find people capable of maintaining and operating it. So If we went for Kafka, and that was a discussion with the Open Data Lab team, the system would have been like super enterprise level, but it would have been very difficult to find and to train the team to be able to work with the system itself, and that wasn't the right choice, because we wanted to have an usable system, not a fancy system. For data storage, we opted for MongoDB because data in for as we said, we wanted to have like a raw data table, which is the data as it is, and because it is as it is, it doesn't have any structure. So no SQL database works really fine. It allows for sharding, which means data can be split among many instances of MongoDB, which makes it really scalable, and allows for replication. For example, Postgres do not allows for sharding. It allows only for replication, and replication means that the same data is replicated on multiple instances. So we have both data on multiple instances and instances which hold just a part of the data, so we have the maximum capability of scaling. It actually is not open source because it's not under an MIT or Apache license, but because we still can deploy a MongoDB cluster without having to go for Atlas Cloud, which is the managed service of MongoDB. We decided it was still a suitable solution, also because MongoDB is one of the most used NoSQL database in the world, so we went for the commodity instead of the strict open source paradigms. Also, if it will be a problem, we can still switch to any other NoSQL database around the world. So after this short, but not really short story, we address the problem of speaking many languages. We address the problem to ensure that no data is lost once it is ingested because of the queues. We handle the errors because of the queues. We also address partially the problem of evolving. We address, until now, almost all technologies are open source, and we did create the raw data lake with MongoDB. So now everything's nice, good, super technology, wow, but how do we actually operate the system? Because as we said at the beginning, when you create something, you don't have just to develop and put it online, but the real work starts once it is online and you need to actually maintain it. So what's container orchestration and why it's even a thing? So in real systems, we can have traffic peaks, so we have to find a way to scale our system, because we don't want the system to go timeout, for example. We don't want it because it's a lot of data. We need to find a way to roll out updates, because, as we said, of course, the system is continuously in development. Fixes will be have to be deployed, and we have to find out a good way to roll out updates. Microservices could become a very lot. Like, just imagine right now the Open Data Hub has, I think, at least 60 providers. If all providers generate 2 microservices, we already have to manage 120 microservices. And I mean, if we go for 1,000 of microservices, 1,000 of providers, and we want to perform like some fancy transformation in the middle, the numbers goes up really fast, and how to manage and how to know which services that deployed on which machine becomes quite hard work. And also, of course, we have to manage the ingress and egress. So internet-facing load balancer, certificates, permission, authentication, and blah blah blah. So a lot of things to do. Docker should be a name everyone knows here. So Docker is the technology to like wrap the microservice inside a small like, package and run it on wherever. So on the cloud, on our laptops, on a server, or whatever. And you could imagine, you could fall in the trap to say, okay, let's containerize everything and then just deploy the containers in the service, like the server. So, like for example, Autostrada A22 goes in machine 1, Tour goes in machine 2, the database goes in machine 3, and we are good to go. But this approach, Docker on bare metal, so without any orchestration, doesn't work very well, because of course, if you start to put manually the application in the service, you lose it. You don't know what is where. You don't have a process to roll out updates. You even have to code yourself the networking, because, for example, if one container has to speak with another, you have to manually put the machine address and blah blah blah. So Docker on bare metal is a good way to start, but a very bad way to continue. So no, this is definitely not. We could use Docker on Elastic Beanstalk at similar. So Docker, Elastic Beanstalk are tools, or maybe technology stack, which some providers like AWS or Google gives to the user, and they basically wrap your container, which is already a wrap of an application, inside a bigger ecosystem, so that you get for free load balancer, auto scaling, replication, secure connection, etc., etc. This is a good approach if you, first of all, you can go for those solutions, and OpenData can't because it's not open source. But also if you manage a small set of microservices, because of course you get a lot, but it means you pay for a lot, and you can actually disable some feature. For example, any container deployed with those tools instantiate a load balancer, which is a service which routes traffic to the actual instances. So that's not a good idea. The evolution of Elastic Beanstalk is our orchestration tools like ACS, which is AWS independent. And those tools allows you to basically abstract the hardware from the software, and basically you manage your container as it was a universe, and you just say deploy this resource, deploy that resource, and make those put those in connection, and you don't actually think about how to do it, like the actuals, like the load balancer, the security group, the privacy policy, and so whatsoever. So that are the container orchestration service you can find around the world, and the one we opted to use because we wanted a system to manage all the all the application without putting a burden to the team. But of course, ICS is proprietary of AWS, so no, because it's not open source. So here we go with our choice, which is Kubernetes. Kubernetes is the most used container orchestrator. It's open source, developed and maintained by Google, and it grants you the ability of horizontal scaling, which means if there is a traffic peak, it spawns another instance of your application, so 2 instances online at the same time. It also manages vertical scaling of cluster, which means if you don't have enough resource, computational power or RAM to manage all your application, it switch on a server, it adds the server to the pool, to the cluster, and it starts to distributing again the pods around the new machine, so that all the application have the resource they need. You won't have a problem of a resource taking all application taking all the resource from the other. As I said, it distributes running application to the cluster, taking account the resource consumption. It also allows to deploy what's called sidecar, which are small applications attached to your application to enhance your application. So that, for example, if you want to have metrics or to collect metrics, you can attach to all of your pods or all of your application a sidecar, which has the task of retrieving the metrics and send it to an Alex stack or whatever. It has rolling update functionality, which means that if you deploy a new version of an application, before switching off the application, the running application, it takes online the new version, it starts redirecting the traffic to the new application, to the new instance, and once all connection and all requests made to the old instance have been closed, it starts destroying the instance, so that you basically have zero downtime running updates, which is quite important for a system like OpenData, since we forecast that there will be a lot of updates and maintenance, the bug fix, the deployment, and whatever. Of course, it also gives you the automatic rotation of the DLS certificate for outside work connection, so with the internet, and also intra-cluster communication, because you can enable HTTPS in intra-cluster communication, and it has the auto-healing functionality, which means that if an application stops to respond, for example, for an error, for a bug, for a deadlock, or whatever, Kubernetes recognizes that that application is not responding anymore and destroys the application and brings online a new instance of the application. And of course, it's open source. So after Kubernetes, we also have somehow addressed the need to be operable. We definitely address the need to be scalable, since we can scale horizontally and vertically. We still have, like, it's not yellow, but still we have a lot of almost everything is open source. We do not have vendor lock-in, and we are almost cloud agnostic. So we are almost at the end, and everything is really nice, but we still have to deploy our thing in a real cloud provider or whatever. I don't know if you are an IT guy, you definitely have seen like this. So to put online a single resource, being it an RDS instance, which is just a Postgres instance in AWS, you have to distribute in a jungle of like thousands of permissions, thousands of security groups. You have to create a lot of resources you don't even know knew existed. And the fun thing is, once you did for that, you also have to do it for production. And are we really sure that we will do the exact things, that like we will replicate all the steps we did for that for production? What if we miss a permission and production goes offline? What if someone, like my colleague, changed a port without me knowing, and the whole product environment goes offline? And here we are with Terraform. So Terraform is a tool which has become how do you say, like a must-have in system and infrastructure like this, which transform the task of creating resources around your cloud in coding them. So Terraform transform a code, like a declaration, you declare what you want, and Terraform do the work of instantiating and creating the right resource. For example, this snippet here, it's like 200 lines of code, and instantiate a lambda, a lambda running a container which is attached to an ACR repository, which sends logs to CloudWatch with the right permission to pull a message from SQS, just with 200 lines of code. And the fun thing is that you can use the same 200 times of code, the 200 lines of code, to instantiate how many lambdas you want. You don't have, like, once you did your package, your model, your deployment, you can replicate as many times you want, and having always the same result. And you can destroy the resource you want, because once you deploy the lambda connected to CloudWatch, connected to SQS, with one single command, you can tell Terraform to destroy everything he created, so that you clean up the whole environment. So no more like orphan policies around your AI, no more things like what's this virtual private network, who did that, why, when, and should I leave it or can I delete it? So this is a game changer if you have to manage infrastructure. So yeah, Terraform gives you resource tracking because you know who, because it's code, so you know who changed that point, because you have the commit, you have to commit the code to run deployment. Who did that change, when, where, and why? And of course you can change it back or destroy the change. You have reproducibility, so that you can copy your dev environment to prod with one single command. You enhance teamwork and revisions, because of course I know what my colleagues did, and they can like approve the pull request on Git before even deploying it. And infrastructure becomes part of the repository, so you don't have, like, you write your infrastructure in the same place where you write what will run on that infrastructure. And of course, it's open source, so we are very happy. Final overview. So yeah, we opted for a distributed microservice architecture, event-driven, Apache Camel for service integration, RabbitMQ as a message broker, MongoDB for the raw data lake storage, Kubernetes for container orchestration, Terra for infrastructure provisioning, and we did our homework, and the whole challenge checklist is done. So for the demo, actually the demo is not easy to visualize. So we created a repository holding the infrastructure we saw earlier. So we create a repository which holds this whole infrastructure in just one repository. You can spin up your Open Data Hub cluster with a Docker Compose, and you can start playing. So just for this is our nice. Okay, so it should. I don't know if it works because I put the computer in standby, so maybe something went wrong. So, for example, the only thing I can show you in 2 seconds is how a message enters the inbound through an MQTT message, so an IoT message. It goes for the message broker. The camel writer writes the raw data in the raw data table. Then the system reacts to the writing of the new document inside MongoDB. It takes control again of the inserted document. It passes the control to a transformer, which is actually a dummy software just waiting for 30 seconds before acknowledge it. And in the meantime, while everything, this whole flow goes through, we also enable a direct republish of the sensor through an outbound MQT WebSocket an outbound WebSocket endpoint. So the only thing I can show you, like in this time, is how a message activates the whole system transparently, and we do have our data saved while the data has been broadcasted to a WebSocket in another place, so it's completely another service, and the transformers take control of the data because he was interested in that message. So, well, so everything's connected, I hope. Okay, so this one's this one is the WebSocket listening for the fast line, which means it's just a repeater for the message, the inbound message. And here we do have another WebSocket which should inform our client that a message has been updated, so he can pull the message, he can pull the new data. Let's send an MQTT. Maybe we should also data. Okay, so drop the collection, so the database is empty. We push a message, which by the way is just a JSON payload. We said that the one pushing this message is the provider A22 with the sub provider Brenner. That might be sensor data from, I don't know, the street or the traffic. And here we are, like in the fast line, we already have our repeated message. We do have our document inside the raw data, the raw data table. And somewhere here we should, at some point, the transformer should time out and publish the message here. So we have just to wait a little bit, maybe. Okay. And the message has been acknowledged because the transformer did the whole transformation, blah, blah, blah. He deleted the message and he pushed the message onto or other WebSocket. So that's how a distributed event-driven system works. So if I had more time, we could go very deep inside the configuration, how you can attach more modules to the architecture to perform more data, but it's not the place nor the time. So last thing before stopping is, so if you're interested, check out the repository, because we put some effort in the documentation of the repository. You have both the guide to spin up the cluster locally with a Docker Compose, or create a Kubernetes cluster in your own cloud. We provided with the whole explanation of each component, how how the data travels inside the infrastructure, so that you can follow the architectural pattern we did, and you can expand it with whatever. So if you're interested, yeah, take a look at that repository. So for now, I'm finished finally, and yeah, if you have any questions.
Thank you, Matteo, for your presentation. So now is the publicum time. Who will be the first in posting a question or a comment?
So thanks for the presentation, it's really great. I would be interested to know what were kind of the original symptoms and problems that you guys saw in the Open Data Hub, kind of the concrete symptoms which made you kind of make the decision we need a completely new architecture, and how does that, I didn't understand if that is already live, how do you see those problems maybe solved or maybe not? Maybe you can share some learnings around that.
So yeah, the symptoms are that the architects, the people responsible of the development of the system were focused more on fixing it and managing it rather than evolving it. So the old architecture, which works fine and it is online since I think 10 years, was made to be online, but not to really evolve in any kind. So if some of the architects here leave Open Data Hub, it will be very difficult to find someone replacing them because everything is so interconnected with each other. So the processes are not well defined. The service responsible of retrieving the data is the same responsible of transforming it and putting it into the database and also serving it. So if at some point a provider needs to change something, you have to rebuild a whole monolithic system. And because of the need of Open Data to scale in the future, to accommodate more providers in a more fast way, in a faster way, we needed to rethink about the architecture itself to accommodate those needs of being modular. People should be well aware of what service is responsible for what and what to touch if something crashes. And that it's not really clear in the current Open Data Hub. And so how this thing helps and heal those problems? Well, actually, you can create, instead of having 60 providers speaking 60 languages and having 60 different transformations sitting on 60 different databases with 60 different protocols and flows, you just have to adjust the connector with those providers. So you just have to speak their language in ingress, and then you can standardize the way the system itself inside works. So once you get the data from a sensor or a PDF document, once it is in the system, you just treat it as the same way. So the PDF generates a message, and the service interested in PDFs starts processing it without the needing of creating a new whole pipeline. So those are the symptoms. I don't know if I actually answered the question. It's really about how the infrastructure, how the system has to be maintained and developed in the future. Because right now, we are not, Open Data is not really going in a I don't know how to say in English, affordable pace. So it's each requirement change implies a big effort, human effort to apply the change to the system. So that's it.
So speed of development and maintainability.
Speed of development, maintainability, and
Was
yeah.
it also performance reasons that some said, hey, look,
well, of course, as we already said, it's not only about performance. You can always have a bigger machine. You can even with container on bare metal, you can have a bigger machine. But once you have not only one application but thousands, you can't have the scalability. It doesn't go only with bigger machine. It's also about smarter machine, a smarter way to handle the application. So The performance might not be a problem now, because of course Open Data works fine because they choose the right machine for the right application. But once you start adding more application, performance might become a problem. Definitely.
I would like to integrate here. So the first, as has been said, is scalability. But also we had this problem of the raw data when we migrated or we updated the data collector. In the time of updating, we didn't save the data. So we lose data because the sensor sends your data, but if you are updating this data collector in this time frame, you don't have the data. That was one very crucial point for us to change the architecture. With the new architecture, every raw data coming in gets saved and then it gets transformed. And even if the transformer has issues, has problems, the algorithm has some bugs, we have the raw data saved now, and so we can recreate the result from the historical raw data which we maintain in the MongoDB, which is the only element which is not open source anymore. Even if MongoDB we know is an open source database, but they changed the license slightly, and it's not open source now, so we will have to see if the architecture is still valid for us, but let's see that. So this was one of the crucial points for us to not have to have a distributed system which allows us to be sure that all the data which comes in gets saved as a raw data table, and then we can create the algorithm.
With that design goal, I mean, that could a monolithic whatever application could do that problem fine as well, and also creating that whole Microsoft architecture would, I think, justify that you say, hey, we just need to store all the raw data and all of them.
Yes, but what happens if you have to update your raw data infrastructure, saving infrastructure? Then we said, okay, we need, it's called sharding. So if the MongoDB has to live on multiple different servers, and in input it has always to get the data. Even if one of these servers crashes, I want to have the data which comes in served and saved.
Yeah,
so
replicating.
Exactly. Yes.
Yeah, okay.
And from then you say, okay, I have to split up the our data collectors at the moment, take the data, transform the data, and save the data. So we started splitting up this, and we introduced the Docker, and then we did say, okay, it's too complicated, we need Terraform, and so, and this is the result.
So yeah, of course a monolithic would have served the same thing, but as you can imagine, a monolithic system goes to a certain point. After that, because in a monolithic system, if you want to attach an AI for whatever reason, you already have to create something completely custom just for that purpose. And if 2 months later you want to having a tagging system to tag the wrong data, you do have to create another custom module or application on top of your monolith, so that you at the end you have a very big monolithic thing with around a lot of things which which will become more and more, and you have to maintain the whole thing while maintaining as a very big monolithic thing system, which process the data, collect data coming from thousands of different sources in thousands of different formats. That becomes of course, that monolithic works, but it's not it's not future-proof, if I had to say.
And just to conclude, you asked also if we match our needs. Actually, we cannot say yes or no because we are at the beginning of the process. We started the migration. We have some services running live, And now in the second half of the year, we will compare also the performance and how it works on the old and on the new infrastructure. And I hope that in 1 year, maybe we can see us here again, and we can explain you how it went this first year of the new infrastructure, also compare with the old one, and so we can do comparison on real data. Actually, at the moment, I do not have the perfect answer to your question. Do you match your goals, because we are at the beginning? So, someone else has?
We didn't get fully the point. You would also like to teach the central database, the PostgreSQL one, or just for the data collector?
No, we didn't present it here in our architecture, the Data Marts.
Yeah.
The single Data Marts will keep the database they have, and we will only in front of them put a MongoDB to store the raw data. And then the transformers take the data, make the transformation, and store it in the, actually we think and we have foreseen to store it in the Postgres databases that we already have in our Animeshon infrastructure, because we do not see any reason to change it.
Also because Data Marts are like the endpoint of the process, and of course, different data maybe want different database, so we can't use, like, we can't say just use Postgres or just use Mongo for everything, because maybe at some point Open Data wants to deal with, I don't know, could be a time series or tracking or monitoring, whatever, and you can't use Mongo or Postgres. You have to use, for example, Influx. So yeah, so Data Marts are at the endpoint, and you can, because of the nature of the architecture, you can attach whatever database you want to that part. Because of course you can, each transformer, each domain of the data has its own transformer and its own storage. Of course, the storage which suits the data the most at the data mart endpoint, because the raw data goes everything in the same lake and stays there.
But the new concept is that you split it up along the parking, media, endpoint. This become different data marts now.
Yes.
That's the
Can.
So that's up to the team, because it's part of, like, it's very specific domain, data domain, and they have to do their assessment there, they choose their choice.
Someone else has some question?
I have a question about the vendor login. Did you decide to actively avoid using features of, for example, MongoDB that are specific to MongoDB, or would you still use those kind of features if you think you can adapt them to other products or vendors?
So the only it's about, the question is about MongoDB specifically.
Well, that's the example.
The infrastructure is designed to be reproducible to any, like, cloud or even like in local. MongoDB is quite different, because the only feature we use of MongoDB, which is MongoDB only, is the event stream, which is basically a stream of events. Basically, you can attach to the op log of the database, so you can read the transaction and know when a document has been inserted inside the database. So that's the only feature we use, which is proprietary of a system, which is it's not agnostic. If we had to get rid of that, which might be also a good idea if we want, we can still have other options, because we just have to either find another database allowing us to touch the op logs, or just publishing the message from using another mechanism. So that's the only thing we are somehow locked in, which is actually very trivial. So yes, to respond to the question, we avoid all the feature which could become vendor locking. Also because there are some regulation we had to meet because Open Data Hub is public administration, so we couldn't use some technologies as well. So that's why.
Thank you.
You're welcome. Someone else has a question or feedback?
I can ask one other question. I would be interested if you can give us an example where you use Open Data Hub in one of your startups.
In one of our startups.
Yes.
In one of our startups here in the Neutech.
No, of yours.
Well, problem is that mine have the same architecture. We can do the same thing like in-house. But I think that whatever startup generates some data could potentially use Open Data, but in any way. Also because if I have to transfer, I don't know, I have a startup doing. I have the startup creating sensor for the Apple field, and I want someone here at the Neutech Park to process my data and, like, for example, giving and inferring whatever metrics, like how the moisture level drops during summer, whatever. I can just throw all my sensor data inside Open Data Hub. And I don't even have to have the contract with the startup, because the data will start flowing inside Data Hub by default. And once we arrange our contract, Stefano can start catching my data in the end. So like starting listening for my provider and start doing its own transformation and put that result wherever and serve to the public. And then someone could use that data again to do some like second level transformation and put again inside Open Data. So the potential of Open Data Hub, not just because of this infrastructure, but because of Open Data Hub, is very high, and that's why Open Data Hub has to meet some like quality, performance, and architectural patterns requirements. Because right now, if I have a startup and I want to push data on Open Data Hub, it's not that easy as you can imagine. We have to first speak with Open Data Hub, then wait for someone to create the custom collector and blah blah blah. So in that way, this architecture make it easier to create interoperability between systems.
Someone else? Otherwise, I would start with the presentation round. Today we are a lot, I'm happy. I kindly ask you to say your name, surname, your affiliation, and 3 words that describes you. I will start as an example, that most of you know me. Stefano Seppi, Neutech Park, part of the Tech Transfer Digital, and my 3 words are Open Data Hub, obviously, open source, and IoT.
Class, please stand up and look at the audience when you present yourself.
Hello everybody, Johannes Brunner from Tech Transfer Unit Automotive Automation. Using the Open Data Hub for our sectoral overview of the innovative automotive companies in South Europe.
Matthias Wallner from High School teacher today for Max Valier. I knew Open Data Hub since nearly the inception 10 years ago of the interim project. And it's interesting to see how it evolved from just collecting the data of the Bolzano municipality. There were just parking data, meteorologic framework, and so on. And now it became such a full-fledged project.
Thank you.
So, hello, my name is Alessandro. I'm a colleague of Matteo. We work in the same startup, Tecnidi. I'm a software engineer. My three words are, I think, software development, entrepreneurship, and innovation.
Thank you. Someone is hiding.
My name is Clement Saga. I'm a software architect at TechPark. I'm working on the Open Data Hub, and I think my three words are open source, open data, and infrastructure.
Hi, I'm Master Mario. I'm here on stage in Data Park, and I worked to improve the graphics of the Open Data Hub website.
Hi, my name is Max Weiler. I'm an AI student and freelancer, and my three words will probably be AI, visualization, and front-end development.
Paid format.
And paid format.
Hi, I'm Enrico Betti. I'm a freelancer and I'm also a software developer. So my three words would be probably curiosity, hacking, and project management.
Hello everyone, my name is Fabrizio and I'm not a software developer, I'm just a colleague of Matteo. I'm the founder of the startup we work together with. And so my three words would be innovation, startup, and I don't know a buzzword about your stuff because it's not really final.
Hi, my name is Martin Romanzo. I'm a business and technology consultant, and my three words are getting innovation done.
Hello, Chris Meyer. I'm a freelance developer and trainer. I don't really have three words, but I'm basically here because I work for NOI, programming some bits of the Open Data Hub. So I was just curious what the new architecture is, and looking forward to implement other pieces for this new architecture. And yeah, that's it.
Hi, my name is Davide Montesi. I'm the founder of the startup Kitchen Salt here at TechPark. And we use Open Data Hub, in this case, the word we are checking the quality of Open Data.
Hi, Diano Marinelli, digitalization consultant for Alpine. My three words would be home automation, IoT, and software development.
Hi, Io Calvanese from the Free University of Bolzano and on topic SRL. And my three words are semantic technologies, virtual knowledge graphs, and on top. System we are developing.
Hi, my name is Lucas Gotta, and I'm software engineer and product manager. I run my own startup, and yeah, since 1.5 years, I'm a little bit back to Italy and to Südtirol. So yeah, great to meet this community here. And my three words are effective meetings, Atlassian, and startup.
Hello, my name is Frederik Platter. I work at the Südtiroler Bauernbund, the Farmers Association of South Tyrol, as a software developer. And my three words are software development, automation, and computational linguistics.
My name is Stefano David. I'm a freelance technical writer. I collaborate with Open Data since 5 years now, writing technical documentation and with other companies in Bolzano and Antwerp.
I'm Fabrizio Wagner, and I'm here by myself. Given the scalability architecture that we saw in this presentation, my three words are site reliability engineering, which is my work. So I appreciate that there was some work on this, because something often is not a concern for developers. In this case, it was an element.
Hi everybody, I'm Lorenzo, software developer at Sidera Software, a small company in Trento. I stay here for my curiosity, and so.
part of the digital network. I'm also responsible for the activity within the software lab. So my three words are free software, agile management, and hackathon.
Okay, hi, I'm Emily. I'm a freelancer and I work with the Unit Digital for some years now. My three words are hackathon, SFSCon, and Open Data Hub Day, which is the event of the Open Data Hub.
Okay, last but not the least.
Okay. Okay, my name is Patrick Gonewijn, Tech Transfer Unit Digital, or Tech Transfer Digital. My three words are the three O's: open source, open data, open standards. And I think now we have a huge party waiting for us outside. Oh, sorry, you didn't present yourself.
Yeah.
Last word.
Matteo Roggia, associate with Animeshon and Technitive. I'm here because this, and my three words are curiosity and go beyond, maybe. Which are three words.
Okay, thank you everyone for being here. I just wanted to conclude just telling you that we are always looking for new contributors. You can contribute in many, many ways. Just also sending us feedback. We have different ways. The main one is if you find an issue or you have a comment, just write at help@opendatahub.com. Or if you want to contribute, just go on GitHub. We have all the entire source code is published there. You find there the documentation and also how to contribute. We will be happy to have you all as contributors. And just before the conclusion, I will launch the next month event. So the 3rd of August, we will have on topic, Diego, your startup, talking. Peter Hofgartner, your colleague, will present how use DuckDB to analyze mountains of data and how this DuckDB has been integrated also in OnTop, which is the product of the startup on topic, which is in the P1 building and spin-off of the University of Bolzano. Now, thank you all for being here. Thank you, Matteo, for the presentation. Now you can enjoy all the rest of the beers you find there, or you can go outside and chat a little bit in front of a beer taken outside. Thank you for coming and hope to see you next month. Bye-bye.
Thank you.
Faccio il 5,